Hello everyone, welcome back to RDCS tutorials. In today's lecture, we are going to continue the deadlock topic with part 2. In the previous video, we studied the meaning of deadlock and the four necessary conditions required for deadlock. Today, we will discuss the deadlock prevention, deadlock avoidance, safe state, unsafe state, and Banker's algorithm. These concepts are very important for UGC NET and PG set and normal MCA and B.Tech and university examinations. Okay, so let's start. So before moving to part 2, let's quickly revise the part 1. So we learned four conditions required for the deadlock. The first condition is mutual exclusion, where only one process can use a resource at a time. The second condition is hold and wait, where a process holds one resource and waits for another. The third condition is no preemption, where resources cannot be forcibly taken back. And fourth condition is circular wait, where processes wait for each other in a cycle. The deadlock occurs only when all four conditions exist together. Yes, this concept we discussed in our part 1. Yes, now let's discuss the deadlock prevention. The deadlock prevention. Okay, what is the meaning of deadlock prevention? The deadlock prevention is a technique used to ensure the deadlock never occurs. Yes, the main idea is very simple. If we break at least one of the four conditions, okay, if we break at least one of the four conditions, the deadlock becomes impossible. We need to break any one of these conditions, either mutual exclusion, hold and wait, no preemption, and circular wait. We need to break at least one condition from these four necessary conditions, then the deadlock becomes impossible. Okay, if four conditions are mutual exclusion, hold and wait, no preemption, circular wait, operating system use a different strategies to break these conditions and prevent the deadlock. Okay, now understand deadlock prevention with a real-time example. Imagine there are four students are there in a college lab. Student A has a printer, student B has a scanner access, student C has a internet access, student D has a plotter access. If each student starts the requesting another student's resource, nobody can proceed. This created deadlock situation. To avoid these deadlock, the lab administrator, what he do? The lab administrator prevents this by enforcing the rules. The rules before he established some rules before allowing the resources usage. Similarly, the operating systems establish the rules to preventing the deadlock. Okay. The next one is preventing mutual exclusion. Okay, now let us see how to prevent mutual exclusion. This idea is to share the resources whenever it is possible. Some resource can be shared among multiple users simultaneously. However, some resource cannot be shared. These are the resources, shared resource, and these are the exclusive resources. However, some resources can be shared, used simultaneously, but some resources cannot be shared. Examples include printers and scanners. These resources we cannot share. So therefore the mutual exclusion can be reduced only for the shareable resources. Only for the shareable resources we are using for the mutual exclusion. Okay. So we'll give one real-time example. So what is the example here? Consider there is some Google Docs is there. Okay, there is some Google Docs is there. The menu is students can read the same document at a same time. Yes or no? The Google documents where the students can read the same document at the same time. At the same time. Now consider a printer If you take an example as a Google Docs, the many students can use the simultaneously. Or else, if we take only one printer, yes, that is nothing but the exclusive resource. The printer is exclusive resource. Therefore, this is the difference between the shareable and non-shareable resources. So here, the only one student can use the printer at a time, but here if you take example as a Google Docs, the students can read the document simultaneously is nothing but at the same time. Okay, this is nothing but the preventing the mutual exclusion. In a mutual exclusion there are two types are there: shareable resources are there and shareable non-shareable resources are there. Okay. Next one is preventing hold and wait. Now let us discuss preventing hold and wait. The hold and wait one, the hold and wait means a process already holds one resource and waits for the another resource. Yes, the hold and wait means the process is holding one resource and it is waiting for the another resource. This can lead what? This can leads the deadlock. Yes, this can lead the deadlock. So we need to prevent this situation. A process must request all required resources before execution starts. What which is the prevention to prevent these situations? The process must request all required resources before execution starts. Or else one more definition is that it will release or held resources before requesting the new one. Yes. So another approach is that the process must release all currently held resources before requesting the new one. This reduces the possibility of resource dependency and a deadlock. Okay. So consider the wedding hall booking example. Before conducting a wedding, people usually book the hall. Yes or no? Before conducting a wedding, they are booking the hall and catering, decoration, photography and together. So they do not book one service and then wait indefinitely for the others. By arranging everything in advance, the conflicts are avoided. Yes, in before the conflicts can avoid. So similarly, the operating system requires the resource in advance to avoid the hold and wait situations. Are you getting my point? Same example we are applying to the operating system. Operating system what it do? The operating system requires the resources in advance to avoid the hold and wait situations. Okay. To the next one. Preventing no preemption. Now let us discuss the preventing no preemption. What is the no preemption? The no preemption means resources cannot be forcibly taken away from a process. This we already discussed. So this we need to. So the resources means cannot be forcibly taken away from a process. The process itself must release them. So to prevent these deadlock situation, the operating system may temporarily take the resources back from a process if necessary. This allows the resources to be reallocated and avoids the indefinitely waiting. We are avoiding here indefinitely waiting. So we'll see one example. The consider there is one classroom projects are there. Okay, there is one classroom projector is there. The faculty member is one faculty member is using that classroom projector. So normally the another faculty member urgently requires this projector. The normally the projector cannot be taken away until the current users finish. Yes. So this is no preemption. So here in deadlock prevention, the resources may be reclaimed when necessary to avoid the what? To avoid the resource blocking. Here we are avoiding the resource blocking. We are using the reclaimed when the necessary to avoid the resource blocking. Yes. So moving to the next one. What is the next one? We are preventing the circular wait. Yes. Now let us discuss the preventing the circular wait. Whenever the circular wait will occur, the circular wait occurs when the process wait for another in a circular form. Yes, in a cycle. So to avoid this situation, the operating system assign an order to the resources. For example, R1, R2, R3 and R4, R3. These process must request the resources only in that order only. Yes, in this order only. This eliminates the circular dependencies and prevents the deadlock. Okay. So here we will see one real-time example, then you will understood. Okay. So what is our real-time example? So, okay, consider there is some school admission process is there. Yes, there is some school admission process is there. Now, what are the students is doing? The students first submit an application, then the verification is takes place, and then after verification, the fees payment is completed. That finally the admission is confirmed. Students cannot jump directly to the verification or admission. So, we need to finish the final step one step by step. So similarly, the process must to follow there is some predefined order is there. There is some predefined order is there. Okay, there is some predefined order is there. That predefined order we need to follow while requesting the resources. Yes, the student first to follow the sequence. They cannot jump the backward. Similarly, the process follow the resource ordering. This we call as a circular waiting. We are preventing the circular wait. It is the next one, the deadlock avoidance. Now we are moving to the deadlock avoidance. The deadlock avoidance is different from the deadlock prevention. Here deadlock prevention is different and deadlock avoidance is the deadlock avoidance is different from the deadlock prevention. Instead of breaking, so in a deadlock prevention, we are breaking the one condition from those four conditions. So here the system carefully checks every resource request before the allocation. Yes, here the main goal is to avoid entering an unsafe state. We are avoiding the unsafe state here. We are avoiding unsafe states. Only safe resources allocations are allowed. So we are avoiding the unsafe state resources. Okay, I will give one example. Consider there is some bank loan approval system is there. Okay, there is some bank loan approval system is there. Okay. So what is a customer request? The first customer is requesting the loan. Before approving it, the bank will check what the bank checks it available funds and future obligations. Yes or no? The loan is approved only if the bank remains financially safe. Similarly, the operating system grants the resources only when the system remains the safe. Okay, when the system remains the safe, the operating system will grants only the resources. Okay, when the system is safe, it grants the resources. Okay, this we called as a deadlock avoidance. So normal deadlock prevention means what? If we break any one condition, we are preventing the deadlock. So here what is the avoidance? Here the avoidance is different and prevention is different. Before approving it, we need to check the before conditions like that. We are using the deadlock avoidance. Okay, instead of breaking the one condition, every resource is requires the before allocation. What is the main goal is to avoid? We are entering the to avoid the unsafe state. Okay. Now, what is the safe state? Safe state is what? A safe state is a state in which all process can complete the successfully. When the processes are complete successfully, then we call as a safe state. Safe says or a safe say sequence exists. A safe is sequence exists. Since all process can eventually finish the execution, the deadlock does not occur, right? Process are completed one by one, there is a no chance to occur the deadlock. The safe state is the desired state of every operating system. It is some desired state of desired state of every operating system. Here I will give an example. Imagine there is some bank is there. A bank has 10 lakhs rupees. Okay, how many rupees are there in a bank? Imagine a bank has 10 lakh rupees. The customers requires what? The customers requires 2 lakhs, 3 lakhs, 1 lakhs and 4 lakh rupees. The bank can satisfy all customers eventually. Therefore, the system remains safe. This situation we called as a safe state. Okay. Moving to the next one. There is some exam point is there. Remember this important exam point. The safe state means what? The safe state means deadlock cannot occur. Whenever that is in a safe state, the deadlock cannot occur. Whenever it is in a unsafe state means the deadlock may occur. Then what is the deadlock state means? The deadlock is already occurred, that we call as a deadlock state. So whenever the safe state is nothing but the deadlocks cannot occur. Unsafe state deadlocks may occur. The deadlock state means the deadlock is already existed. This comparison is frequently asked in competitive examinations. Okay. The next one is safe sequence. Okay. One more concept is there. The sequence. Sequence is nothing but what? There is an order. Sequence is nothing but the order. Yes. Sequence is nothing but the order. So a safe sequence is an ordered execution in which all process complete successfully. There is some order of execution in which all process complete successfully. For example, P2, P1, P3 and 4. If the process execute in these order and all complete successfully, the sequence is considered as a safe. This we consider the sequence is safe. Okay. So I'll give an example. Consider there is some operation theater is there. Okay, in a hospital, there is one operation theater is there. The patient 2 is treated first, then patient 1, then patient 3, then patient 4. Even every patient received the treatment successfully. Yes, this order is similar to a safe sequence. Okay. So you just remember this important concept. Not every unsafe state becomes deadlock. Okay. Not every unsafe state becomes deadlock. However, every deadlock state is considered a every deadlock state originates from an unsafe state. Therefore, the unsafe state is considered a warning state here. Not every unsafe state becomes deadlock, but every deadlock state originates from an unsafe state. So, these unsafe state we consider as a warning state. Warning state. Okay. Now we come to Banker's algorithm. The algorithm was developed by Edward Discustra. Okay, it is one of the most important deadlock avoidance algorithm. The Banker's algorithm is one of the most important deadlock avoidance algorithm. What is this algorithm? This algorithm determines what? The algorithm determines whether a granting a resource request will keep the system safe. Okay, whether a granting a resource request granting a resource request will keep the system safe. Will keep the system safe. Okay, will keep the system safe. So this is the example. The developers the Banker's algorithm is Edgar Discustra. So moving, why this bankers algorithm? The purpose of bankers algorithm is what? The purpose of bankers algorithm is to avoid a deadlock, maintain a safe state, and allocate the resources safely. What is the main? It will maintain the safe state and it will allocate the resources safely. Before granting the resources, the operating system will check whether the allocation keeps the system safe. Before the granting these resources, the operating system will do, the operating system will checks whether the allocation is keeps the system safe. Only then our resources are allocated. Okay, our resources are allocated. Okay. So there is one example is there. There is some bank manager is there. The bank manager before approving a loan to the customer, it will check the available money. Then if the money is there, it will check the future commitments. Then it will approve the loan if only the bank remains safe. This we call as a banker's algorithm. So next one, the data structures used in Banker's algorithm. So Banker's algorithm will use the four important components. There are four important components are there: allocation matrix, maximum matrix, need matrix, and available vectors. These structures help the operating system to determine it will determine whether the system remains safe after resource allocation. We'll check whether remains the safe. The operating system remains safe after resource allocation. Okay. So what is the exam point of? Remember these four terms. The questions are frequently asked from them. What is the four components? Allocation matrix, maximum matrix, need matrix, and available vector. So we'll see one by one. What is the allocation matrix? The allocation matrix shows the resources currently allocated to the process. It will shows the currently allocated to the process. For example, P1 has two resources and P2 has one resource. This matrix tells us how the resources are currently distributed among the process. How these resources are distributing among the processes. Okay. So one example, there is some libraries. So that student A borrowed two books, student B borrowed one book. This information is similar to an allocation matrix. There is some information is there that is nothing but the allocation information. The next one is maximum matrix. The maximum matrix is what? The maximum matrix is represents the maximum resources required by each process. The maximum resources are required by the each process. For example, P1 may require 7 resources, P2 may require 5 resources, P3 may require 3 resources. This information helps the operating system predict the future resources requirements and make the safe allocation decisions. Okay, will predict the future resources. What is that? Predict the future resource requirements. Resource requirements. Okay, predict the resource requirement and make the safe allocation decisions. Okay. So what is the real time? There is some wedding function is there. The wedding function, the maximum guests are there, 500 guests are there. The estimation guest is 500. Even if only 200 guests are arrived initially, the planning is done for what? The planning is done for the 500. Okay, this we call as a maximum matrix. Moving to the next one, need matrix. What is the formula for the need matrix? The need matrix is nothing but the maximum minus allocation. There is some example there. The student needs only 10 books. So already received what? 6 books. Need is what? 4 books. Simple, we are subtracting. 6 minus 4 is what? There is nothing but the formula. Need is student needs 10 books. and already received what? There is a 6. 10 minus 6 is 4. The need books is 4. So this is the formula for the need matrix. So need matrix is tells what? That tells us how many additional resources are required by a process to complete the execution. It tells what? The need matrix will tells how many additional resources. Okay, how many the additional resources are required by a process to complete the execution. Okay, the need the formula is very simple. The need is equals maximum minus the allocations. Okay, need is equal to maximum minus allocation. Suppose a process requires a maximum of 10 books, right? So currently it is already has 6 resources. The need matrix is one of the most important concept for the banker's algorithm. So what is the remaining here? The remaining is 4. This we called as a need matrix. It is very important for the banker's components of a banker's algorithm. Whenever we solve the numerical problem, the first step we need to calculate is need matrix. Whenever there is some numerical problem is there for the banker's algorithm, that we need to calculate. The first thing is what? Need matrix. Okay. The student will remember this formula because it is frequently asked in UGC NET and TG set exams. Okay. The next one is available vector. The available vector is what? The available vector represents the resources that are currently free and ready for the allocation. Available vector is nothing but the resources are free. Okay. The resources are free. They are ready for allocation. Okay, when the resources are, it is free, so they are ready for the allocation. These resources are not allocated to any process. Before, these resources cannot allocated by any process. For example, library contains 100 books. Okay, it contains 100 books. Total library 100 books are there. Out of these, the 80 books are issued already, the remaining 20 books are available. So similarly, the available vector stores the number of resources that can be allocated immediately. Before granting a request, the operating system always check the available vector. Okay. The next one, the steps of banker's algorithm. It is very important. The complete working of banker's algorithm. Step 1, we need to calculate the need matrix. Need equals minus. What is the need matrix? Need, it is equals to maximum minus allocation. Yes, maximum minus allocation. This is the formula for the need matrix. The step 2, what is the step 2? We are checking the available resources. The operating system verifies whether there are some enough resources are available or not. What is the step 3? We are finding the safe sequence. The system, safe sequence means the system tries to identify a process that can be complete execution using the available resources. What is the fourth one? The grant request if safe. If the allocation causes an unsafe state, the request is postponed. So if the allocation is free, the allocation is safe, we are granting the request if safe. This is how banker's algorithm avoid the deadlock. The UGC net pointers always solve the banker's algorithm step by step. Do not skip the need matrix calculation. Okay. So we'll give one numerical example for the banker's algorithm. So here there is one important example is that these are the processes, these are the allocations, and these are the maximum. We have three processes, P1, P2 and P3. So P1 allocation what? It allocation 1, P2 allocation 1 and P3 allocation 1. From process P1, the allocation is equal to 1 and the maximum equal to was the maximum is equal to 4. The need equals 4 minus 1. Yes, What is the need formula? The need formula is maximum minus allocation. For the process P1, what is the maximum? 4. The 4 minus allocation is 1. So what is the need equals 4 minus 1? The answer is which is 3. So for process 2, the allocation is 1, maximum is 1. So what is the 3 minus 1? So what is it needs equals to 2. And the maximum, the allocation 1, maximum is 2. The 2 minus 1, it is equal, the need is equal to 1. So maximum. So after calculating need matrix, we move to the next step of finding the safe sequence. Okay. So again, exam team, always calculate the need matrix first. Most students lose marks by skipping this step. Okay. Now finding the safe sequence. There are available 3 is there. Okay. Available resources are there. How many available resources? There are 3 available resources are there. We check which process can finish the first. The P3 requires only one request and P2 requires 2 and B1 requires 3. So since available resources are 3, the P3 can complete. After completion, the P3 is release its resources. After available resources increase, now P2 requires what? P2 requires 2 processes. Again, resources are released. Finally, P1 completes. So here, therefore, the safe sequence becomes first. Which one is the smaller? The P3, it is P3 release, if after completion of P3, it releases the resources. Now P2 requires 3 resources. After completion, it releases the P2. Now P1 is requires 3. So after completion, after completion of P2 resources, it will release the P1 resources. Yes. So finally P1 will complete. Therefore the safe sequence becomes P3, it is followed by P2 and it is followed by P1. Since all processes are complete successfully, the system remains in a safe state. Yes, the system remains in a safe state. Okay. So UGC NET Important MCQs. It is revised through the important multiple choice question. The question number 1, Banker's algorithm is used for which one? The Banker's algorithm is used for scheduling. It is used for deadlock prevention, deadlock avoidance, and paging. The Banker's algorithm is used for the deadlock avoidance. What is the next one? The need matrix formula is maximum minus allocation. What is the formula for the need matrix? Maximum minus allocation. So these are very important objective questions and frequently appear in competitive examinations. Okay. The third question number 3. Who developed the Banker's algorithm? Turning, Discustra, North and Dennis Ritchie. The Discustra is the correct answer. So safe sequence indicates what? The safe sequence indicates the safe state. Students should practice such questions regularly because they are frequently asked in UGC NET and TGCET examinations. Okay. So let us summarize today's lecture. We studied what? We studied deadlock prevention. We learned how to prevent the mutual exclusion, hold and wait, and what is that? No preemption and circular wait. Then we discussed the deadlock avoidance. We understood the safe state, unsafe state, and safe sequence. Finally, we studied the Banker's algorithm along with its important components such as allocation matrix, maximum matrix, need matrix, and available vector. We also solved a numerical example and identified a safe sequence, right? Yes. So thank you for watching this lecture. I hope you clearly understood deadlock prevention, deadlock avoidance, safe state, unsafe state, safe sequence, and Banker's algorithm. If this video helped you, please like, share, comment, and subscribe to RDCS tutorials. In the next lecture, we will study deadlock detection and deadlock recovery, which are also important topics in operating systems. Until then, keep learning and keep preparing for UGC NET and TG set. Thank you and all the best.